All right, I wanted to add a little something to that to this last video clip. And by the way, I apologize for the sound quality in the last few recordings. I had a headset that I had used for years that just died, and I've been experimenting with replacements, and I've been having really bad luck with sound quality for the last couple months. So I think this configuration will work better for sound. All right, I wanted to discuss something a little bit on the advanced side. The good news for you is that you're not going to be tested on this week. But I think it might be a good chance to kind of ease into it if we can start looking at this concept now, because it fits into what we just talked about, and it will be important later. So to demonstrate what I'm talking about here, I want to get a sense of some factors that affect the standard deviation, or the width, of that binomial distribution. And I found a different app that really works better for this demonstration. This is on geogebra.org. But one issue, it's a subtle issue, but it's basically required for this discussion, is that the way we've been talking about the binomial distribution is that the x-axis is numbered from 1 to, like, let's say 10, if we're talking about samples of size 10. You can have anywhere from zero, I should say, anywhere from 0 successes to 10 successes, and we've been counting those as whole numbers of successes. What we're actually going to be doing moving forward in this class is that we're going to be converting these whole numbers into fractions, because they are going to represent proportions. So, for example, if we had a sample of 10, and it had, let's just say, 6 successes in it, then that means that sample has 6 out of 10. It has a success rate of 6 out of 10, right? Which is, let's just call it 0.6 as a decimal, or 3/5 as a fraction. So if what we basically have to do is divide all of these numbers by 10, so then they'll become 0, 1 out of 10, 2 out of 10, 3 out of 10, dot, 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 10 out of 10, or 100%. And those will represent the proportions of the samples, proportions of successes in each of the samples. The reason we like to do that is because now, no matter how large n is, you can kind of imagine that this x-axis will always be scaled from 0 to 1. So that we can compare them very easily to each other. And what I'm doing here is I'm sliding this slider to increase n, and this makes it very clear that, again, if you imagine this scale as always being numbered from 0 to 1, you can see that this distribution keeps getting narrower and narrower. All right, when n, this app goes up to n equals 100. So again, if we took smaller and smaller samples, this distribution gets wider and wider until, in the very extreme, it becomes totally uniform, very wide, and not bell-shaped at all. Pay attention again as we increase n. Not only is the distribution becoming narrower, but it's also becoming less blocky and more smooth. So you see how these basically look like stair steps, right? They're very discrete. If we increase the sample size, 5, 6, 7, 8, 9, 10, you can see that these stair steps become smaller and smaller and finer, and they're starting to fit this smooth, continuous curve better and better. So by the time you get up into close to n equals 100, it's kind of almost hard to tell with the naked eye anymore that it's not a smooth curve. And very often in statistics, we take samples of in the thousands. So you can just imagine how smooth this would become if it represented a survey of 1,000 people. Okay, so that's issue number 1. The larger n gets, the larger the sample size gets, the narrower the curve becomes, which means that it has a smaller standard deviation. Okay, so again, you have some time to think about this and digest it. You're not going to be tested on it this week. It's just a concept that is going to become an issue later. So I'd kind of rather start taking these things one step at a time instead of just dumping everything on you at once when it comes up next week. Okay, The other issue is that the width of the curve is also maximized when p, the proportion of successes, is 0.5. And that's not intuitive at all. It's also a little bit harder to see. But let's see what happens, for example. Let me actually decrease the sample size so we get a wider curve. Let's just take it down to about n equals 15. Okay, so you can see here that when p equals 0.5, this curve is pretty wide. And if we decrease p, obviously the curve shifts to the left because now only 25% successes. We would only expect about 25% of the of the values to be successful. But not only is it shifting to the left, again, it's kind of hard to see, but it's actually becoming narrower as well. Maybe it's easier to see at the extreme level. Okay, see how that curve is pretty narrow now? When we take it closer to the middle, it does get a little bit wider. That's not a huge effect, but that's just the other thing that I want you to think about today.